As I said, it's been a long time since I gave a talk from a podium in a seminar room. And so I'm not quite used to that. And we're also experimenting here with new technology. So let's hope that things work out. I also got a few questions by email from people. I encourage more questions, but I wish I got more. That's what I got. And therefore, I decided to start this talk with a summary of the end of last talk. So in the previous talk, which was earlier in the week, we discussed standard theories. This is the model known as the XY model in 2 dimensions or in 1+1 dimensions. It's one of the most studied quantum field theories ever. And I think it's fair to say that there are tens of thousands of papers on it. And I couldn't give a complete presentation of it. And not only that, I presented it from a new perspective, a perspective that will help us in the rest of these talks. So the action that we use, we presented it on the Euclidean 2-dimensional lattice with periodic boundary conditions. Phi is at the sides of the lattice, and it is circle valued, so phi is identified with phi plus 2 pi. But instead of writing the action using cosine, we presented it in what is known as the Villain form, where phi is real valued, and we have a gauge symmetry that shifts phi by an integer. By doing that, phi becomes effectively circle valued. And in order to implement that gauge symmetry, we put integer valued gauge fields on the links n mu. So n mu is a dynamical variable with sum over it on the links, and phi is real. And the original XY model is essentially this term here. And so we set kappa to 0, so we can ignore this term. And in the UV, we have a 1-parameter family of theories labeled by beta. And at long distances, it flows in the infrared to a free compact boson, a theory known as the C whose 1 model, which is also very widely studied. And this statement is true provided beta is large enough. Depending on the units, the transition happens at different places. Using the high energy convention, we use R. The transition is at root 2. For large R, this model is gapless, and it describes the motion of these plane waves of phi's. And it also has what we call momentum and winding states where the 0 mode of phi has some momentum, and also phi can wind around the circle. At smaller values of beta, or at smaller values of R, this model is actually gapped, and it flows at long distances to a gapped system, which is a trivial gapped system. Then we deformed the model, so we presented the 1-parameter deformation of this model by adding another gauge invariant term, which is essentially the field strength or the curvature of the integer valued gauge field n mu. And we were particularly interested in the limit as k goes to infinity, as kappa goes to infinity. As kappa goes to infinity, the gauge field n mu becomes flat because it forces this term here to be 0 because kappa is infinite, and we have e to the minus kappa times this term in the action. And as kappa becomes large, every configuration where n is not flat gives 0 to the functional integral, and we can forget about it. And then the model with kappa equals infinity was analyzed using a trick. Instead of having a parameter kappa with this term, we added a dynamical field, which we denoted by phi tilde, which implemented the constraint that this thing vanishes as a Lagrange multiplier. And the resulting theory is denoted here in this brown line. It's also a 1-parameter family labeled by beta, which is what this theory does as kappa is infinite. And it flows at long distances to in the IR to this compact boson theory for every value of beta. And unlike the original theory, this one, that does not have the winding symmetry, it has only the momentum symmetry. The theory with infinite kappa has both the momentum and the winding symmetry, very much like the continuum theory. So it's a different lattice model, but the main advantage of this lattice model is that it is very close to the continuum theory. It exhibits almost all the symmetries of the continuum theory, and in particular the momentum and winding symmetry. And it also exhibits an anomaly that exists between them that had been known to exist in the continuum, but now we reproduce it already on the lattice, so there is no reason to doubt that this is correct. I remind you this immortal line that the continuum is slippery, and slippery as it is, this model gives us a completely rigorous way of presenting the continuum theory for including the momentum and winding symmetries and the anomaly between them. Also, if we use Poisson resummation on these integers n, we find that the model is exactly self-dual, another interesting property of the continuum theory. So this is a lightning review of the first lecture. Are there any questions so far? No.
No questions.
So, yeah. Okay, so armed with this understanding of known theories, we are ready to move to more interesting theories, more modern ones. And instead of jumping all the way to fractals, which have many new elements, I decided to focus on one of them, one exotic theory. It actually does not have fractals, but it has some of the peculiarities that theories of fractals exhibit, and in particular, it has a subsystem symmetry. So recall what we did in the ordinary XY model. We started with a model with a cosine and its symmetry. Then we wrote a continuum Lagrangian, continuum action. We analyzed the continuum action using continuum techniques. But if one is not comfortable with this, we presented another lattice model, which is a good regularization of this continuum model. So we're going to follow exactly the same strategy here. And the model we're going to discuss was first discussed by Paramakanti, Balance, and Fisher, and a lot of follow-up on that. They presented it in a Hamiltonian formulation. Time is Lorentzian, and there is a Hamiltonian. Phi is circle valued at the sites, and there's a potential term, cosine delta x delta y phi. This is a linear combination of phi's around the plaquette with different signs, plus, minus, plus, minus. So it's a linear combination. And in their model, the Hamiltonian has a momentum square for each sites. In the Euclidean version, we have a cosine in delta tau phi. This is roughly the time derivative of phi, or the velocity of phi, and we need the cosine because phi is circle value. So now we have a functional integral, which if Euclidean time is finite and space is finite, we have a finite number of variables to integrate over phi. Every one of them is circle valued, so we have a finite dimensional integral to perform. And the action is bounded, everything is nice. The functional integral converges, and we get nice answers. Then we could ask whether the continuum limit makes sense, but at least the starting point is absolutely rigorous. It's a well-defined integral. So before we analyze it further, let's discuss the global symmetries of this system. And I'm going to follow exactly the same reasoning as in my talk on Monday. So this system has a subsystem global symmetry. Notice that phi depends on x hat, y hat, and tau hat are the integer values of the coordinates of my lattice, of my Euclidean lattice. And I can shift phi by an arbitrary function of x plus an arbitrary function of y. Not just a constant, I can put an arbitrary function of x here. And notice that this term is invariant because delta tau kills these things. And this is invariant because delta x, delta y kills these terms, kills also these terms. So there is a huge symmetry, and the number of elements in the symmetry is the number of sites in the x direction. These are the number of different parameters that we have here, plus the number of parameters in the y direction. This is the number of parameters here. This is Ly. And we have to subtract 1 because we don't want to count this constant mode twice, once here and one here. Now, for simplicity, I'm going to set space to be a square rather than a rectangle, and this will simplify some of the equations. So this is our model, and now we're going to take its continuum limit, or if you wish, its low energy limit. Are there any questions about the model? No. Please interrupt me with questions because otherwise I'll make a threat. If you don't interrupt me, I'll go faster. So I'm going to take a limit. So I'm going to assign lattice spacing. In the time direction, it would be a sub tau. In the space direction, it would be a. And knowing how things are going to scale, I'm going to set them to 0 such that a tau is proportional to a squared. This I'm going to take them to 0. I'm also going to take the number of sites in the time direction and in the space direction. I'm also going to take them to infinity. So there will be more and more sites. The distance between them will be smaller and smaller. And I'm going to hold the overall length of space and the overall length of time fixed. And when I assume that these pies are sufficiently smooth so I can expand the cosines, and I'm going to define parameters mu0 and mu, depending on these lattice spacings, and I take the 0 and I land on this Euclidean action. So what I'll do in the coming slides is analyze this Euclidean action. So this is a free field theory. It's quadratic, unlike this model that has cosines. This is quadratic, so it's free, it's easier, and phi is circle valued, and we're going to analyze this theory as a candidate for the long distance behavior of this one. So the discussion is very similar to what we did in the XY model, not the XY plaquette, the XY model last time. It's free. And the first surprising thing that we have is that because of the derivative structure, some field configurations that are not smooth are not suppressed. Imagine phi is an arbitrary function of x and tau plus an arbitrary function of y and tau, which is smooth in tau, but discontinuous in x and y. Nothing in the continuum action, let me write it again, nothing in this continuum action is going to suppress such configurations. So this is the first thing we'll learn, that this action makes us face in question of how should we address, how should we deal with such configurations that are not continuous. We also discussed the subsystem symmetry on the lattice, and since it exists on the lattice, we should look for it in the continuum description. And since it exists in the continuum description, there must be a nether current for it. And the nether current turns out to satisfy the following differential equation, the following conservation equation. So I'll call it momentum symmetry, and it has a time component to the current and a space component which has indices x, y. In terms of the fundamental degrees of freedom, the time component is the time derivative of phi, and the space component is dx dy phi. And it satisfies the equation of the conservation equation, this equation, which is nothing but the equation of motion of phi. So the equation of motion of phi leads to Nether's conservation equation. Now we see here something that we are not used to in conservation equations and Nether theorem. We can take these currents, this J0, and integrate it only over y or only over x. We don't have to integrate it over all of space. We can integrate it only over a line, and it is conserved, because if I hit this by d by dt, d by d tau, if I'm in Euclidean space, I have here d by d tau acting here. I use the conservation equation, dx dy jxy here, and then the derivative I can integrate by parts, and I get that the time derivative is 0. The way it acts on the field, it shifts phi by an arbitrary function of x plus an arbitrary function of y. So in the continuum, this is an infinite dimensional symmetry group. The group of transformation is infinite dimensional because we can shift phi by an arbitrary function of x plus an arbitrary function of y, including discontinuous functions. Furthermore, we have another symmetry, which we'll refer to as winding symmetry, analogous to what in the previous case was referred to as vorticity, and that's an emergent symmetry, a symmetry not present on the lattice, but it does exist in the continuum. And its nether current is the following. So this is very similar to what we did there. I will not repeat it again. If we have symmetries, we have currents, momentum or winding or whatever, we have nether currents. There's a clear procedure what it means to couple them to background, to gauge fields. And this is something that was already understood in the 19th century. If you have a current J, you add to it, you add the vector potential A, and you write J dot A, and this is how you do it to leading order in A. So if you have a system with a global symmetry, it's at least to leading order in A, there is a well-defined recipe how to couple it to gauge fields. And what will happen here is that the first thing we'll do is we'll couple it only to classical background fields. We're not going to integrate over these fields. This is something that will come from outside, and we couple the system to a background field and see how it reacts to it. And later we will study the dynamical gauge theory of these gauge fields. So we'll do it in 2 steps. So we had a Lagrangian in the continuum, and we would like to couple it to background fields. And this is very similar to what we did last time. First, for the momentum symmetry, I'm shifting phi dot by a tau. And I'm shifting dx dy phi by axy. So I'm introducing 2 background fields, axy and a tau. And I take the kinetic term, this is going to be invariant, and this is going to be invariant. And I'm also adding another background field for the winding symmetry, the emergent symmetry, which multiplies using the netted current that appeared on the previous slide. So now let's check the gauge symmetry. We can shift phi by an arbitrary function of x, y, and tau. Notice this is a gauge symmetry for the background field. This is not a true symmetry of the system because A, in the quantum theory that we study, A is frozen. It has fixed value. And now we ask how the answers depend on that fixed value. So I can shift phi by an arbitrary gauge parameter, alpha, which depends on x, y, and tau. And I'm shifting A, tau, and axy as here, e by d tau, dx, dy alpha. And you can check that this term and this term are invariant. So this is what we mean by a tensor gauge theory. Now I'll say more about tensor gauge theory later, but here I just follow my nose. I have a system that has a subsystem global symmetry. I couple it to background field. I started with U1. With discrete symmetry it can also be done, but then more work is needed. But here it's easy. I just have the current times the gauge field, and the gauge transformation are dictated from the conservation of the netted current. So this term and this term are invariant under this gauge field. What about A tilde? A tilde was the gauge symmetry, the gauge field for the winding symmetry, and it has similar gauge transformations with a gauge parameter alpha tilde, which also depends on x, y, and tau. And again, I couple the current to the gauge field. However, when we try to check gauge invariance, this term is invariant, this term is invariant. This term is invariant under alpha tilde transformation, but not under alpha transformation. So the action transforms by what can be thought of as the field strength or the curvature of the gauge field A tilde. In other words, we have a 't Hooft anomaly between this momentum and winding symmetry. It's quite analogous to the 't Hooft anomaly I presented last time between the momentum and winding symmetry of the ordinary XY model. Here we see that this model also has 2 such symmetries, and there is an 't Hooft anomaly between them. Let's quantize this system. So turn off A tilde. We have just a system with the scalar field phi, and we try to quantize it. And we follow the same strategy as on Monday. So the model depends on x, y, and tau. I forgot y here. And we have phi of x. So what do we have? We have plane waves. We substitute plane waves with coefficients that can depend on time. This is nothing but a change of variables. I'm not doing any dynamics or anything special. I sum over all the modes such that neither kx nor ky are 0. So we have such plane waves. And then we have all the modes that either kx or ky is 0, which appear separately here. So when we quantize the system, we take this decomposition. This is what's called normal modes. So when you study harmonic oscillator, it has various names. We take this, substitute it in the action, derive the Hamiltonian, and we follow the standard quantization procedure. These modes are relatively easy to quantize, and these are plane waves. They are characterized by integer kx and ky, the integer values of the momenta in the x and y direction, and they have frequency omega, which is obtained from the action or from the Hamiltonian. These are the frequencies of the harmonic oscillators of these A's, and they are proportional to kx, ky over L to the fourth, or the momentum in x. So omega square is proportional to the physical momentum in the x direction times the physical momentum in the y direction. It's not like in standard systems where the frequency is proportional to the momentum. Here, the frequency scales like the momentum square. And more specifically, it's the momentum in x times the momentum in y. And this is going to lead to all sorts of interesting properties. For one thing, these k's are integers, right? We have integer number of fluctuations or changes of the wave function between our box with periodic boundary conditions. And since we have non-zero kx and non-zero ky, the lowest energy modes, the lowest frequencies, scale like 1 over L squared. See, we have omega squared is proportional to 1 over L to the fourth. We take the square root of it, and so omega scales as 1 over L squared. Which normally, this is 1 over L, because normally the frequency is proportional to the momentum, which scales like 1 over the length of the system. Here it's proportional to 1 over the length squared. This will be very important. Second, for very large L is the size of the system, we can have low frequency with arbitrarily large momentum. The physical momentum is the integer divided by the length of the system. And this is another peculiarity of this system. Normally, we are interested in low energies. So we can ask what happens in very low energies. And normally, omega is proportional to k, in k over a. So at very low energies, we have very low wavelength or very low momentum. Here, at low energies, we can have dependence on arbitrarily high momentum. So if px, if py is sufficiently small, arbitrarily large kx leads to small omega. So low energy physics gets contribution from very arbitrarily high momentum modes. This is very unusual. Low energy physics normally depends on low momentum. Normally when we discuss the renormalization group, when we discuss what happens in the system as we go to low energies is the same as long distances. What we see here is that we go to low energy, we still have dependence on what happens at very high momentum. We refer to this phenomenon as UV-IR mixing, and this is really quite peculiar and goes against everything that anybody who studied any field theory is familiar with. Normally, this does not happen in field theory. Normally, in field theory, what happens at long distances is independent of the details at short distances. Here we see that the low energy physics depends on short distance physics. And this is related to all sorts of other phenomena that we're going to see. Going back here, we discussed the non-zero modes. These are these plane waves. What about these modes, the zero modes? Here, either x, this mode is independent of y, and this mode is independent of x. As such, they are charged under what we call the momentum symmetry. The momentum symmetry, recall, shifted phi by a function of x plus a function of y. So if we shift phi by a function of x, it shifts this mode. If we shift by a function of y, it shifts this mode. So they look like this momentum symmetry, this subsystem symmetry is spontaneously broken because phi is shifted by the symmetry. However, we'll soon see that that's not the case in the quantum theory. And in the quantum theory, this subsystem symmetry is actually restored. I add here parenthetically that when we studied the compact boson here on Monday, we also considered the mode which was linear in x or linear in y. These are the standard winding modes of the compact boson. We don't have to consider them here separately because they are included in these guys. So we shouldn't discuss them separately. Now let's quantize these modes. These two modes share the zero mode because the constant phi, which depends only on time, when we write it as a decomposition, function of x plus a function of y, we shouldn't count it twice. But let's ignore these things, otherwise it will only clutter the equations, it will not change the qualitative features. And if we ignore this fact, the first mode and the second mode decouple from each other. So our action looks like this. So what did I do? I took the decomposition on the previous slide, and I simply substituted that in the action, and this is the effective action of these zero modes that we should study. This part has an integral d time, we are used to that, and here we have an integral dx, but notice that there is no x derivative. Similarly here we have an integral dy, but there is no y derivative. This is unlike the ordinary compact boson. How should we think of such a system? If we look at this term, we have at different values of x, we have a rotor. A rotor in the sense that phi is 2 pi periodic, it's circle value. So we need to quantize this mode. But we have a separate rotor for different values of x. These rotors do not talk to each other. In order to analyze it more carefully, let's restore the lattice. And if we restore the lattice, we get a factor of 1 over n. We'll go to the Hamiltonian. We get a factor of the lattice spacing in the denominator. And this n is the integer valued momentum, which is conjugate to phi. So if we restore the lattice at every point x and at every point y, we have a separate integer, which is the value of this momentum of the subsystem symmetry. And notice something peculiar. If we try to restore the continuum limit, namely hold mu0 and L fixed and A going to 0, all these energies of the rotors go to infinity. So classically, we had lots and lots of zero energy states because we can let phi rotate. So imagine phi is independent of x but depends on y. So I pick one value of y and I let this phi rotate. So all these phi's rotate simultaneously, and this is the action of this momentum symmetry, and it looks like it's spontaneously broken. We are used to the fact that the symmetry that appears spontaneously broken classically is restored quantum mechanically. Not only is it true here, but here it's true by an infinite amount. So all the modes charged under this momentum symmetry actually have infinite energy. So this momentum subsystem symmetry was broken in the classical theory, but it is restored in the quantum theory. What about the winding symmetry? I also discussed the possibility of having a winding symmetry. So if we would like to have a phi that activates this winding symmetry, recall that its current was d by dx, d by dy phi, and it has to be periodic. This is a typical function that we can study with a Heaviside theta function here and here. Don't pay attention to the details. The important thing about this configuration is that the winding charge has a delta function in x or a delta function in y. That already looks a little bit singular, and to quote the great man, looks slippery. And indeed, these configurations have infinite energy. If I restore the lattice spacing, their energy is of order 1 over A. And the reason for that is that the field phi is discontinuous, and we have x times theta of y. So when we compute the double derivative with respect to x and with respect to y, we get these delta functions. And when we square it and put in the action, we're going to get delta of 0. So that's bad, and that gives us infinite action. This will be important soon. So what I'm really saying is that when we just follow our nose and analyze this phi theory, we have plane waves with energy of order 1 over L squared. This is unlike the 1 over L. We have states charged under the momentum symmetry with energy first 1 over A, but there's also an A in the denominator, the lattice spacing, and the one state charge under the winding symmetry also has 1 over A and A in the denominator. So in the continuum limit, only the plane waves survive, and the momentum and winding states, which exist on the lattice, but they are all pushed to infinity and are not present in the continuum theory. So strictly speaking, the continuum theory has the symmetry, has the conserved current, but does not have the charge states, which is also quite peculiar. We can also work, as in the compact boson, and realize that there is T-duality. The theory of phi has a duality transformation that exchanges mu0 and mu, and exchanges phi to another phi, and it exchanges the momentum and winding symmetry. And these defects, or these winding states and momentum states, are being exchanged, those with infinite energy, are being exchanged by this symmetry. So these manipulations of the phi theory might look very suspicious, because they have all the standard problems of a continuum field theory, infinite non-continuum of degrees of freedom, possible divergences, and so forth. But in addition to that, here we have all this business of dealing with discontinuous functions. How exactly should we deal with these discontinuous functions? What exactly are the rules? How should we treat these momentum and winding symmetries? How should we think of these states with infinite energies? In other words, we discussed all these phenomena of winding subsystem symmetry, which did not exist in the... So, first of all, the continuum analysis might look suspicious. Second, it exhibits some properties which existed already on the lattice, like this momentum subsystem symmetry. That we can live with. But it also has this winding subsystem symmetry, which was not there on the lattice, this 't-Hooft anomaly, the self-duality. How should we deal with that? And I'll be that here brief, because I'll basically follow the same route I followed on Monday and treat this theory in a different way, using this Villain formulation. And I'm going to give what is a manifestly rigorous treatment of this theory in a way that exhibits all these interesting features already on the lattice. So we start with this model that I discussed, and I'm going to write it in a Villain form. So instead of having cosine, I'm writing squares, and phi, which was circle valued here, it will be real valued here, but I'm going to add a gauge symmetry that shifts phi by an integer. So earlier we discussed this background gauge field, A tau and A sub x, the gauge symmetry of the tensor gauge fields, of this gauge symmetry of the subsystem symmetry. There it was the group was U1, now the group is Z. So I'm adding integer valued gauge parameter k at the sites. N tau is shifted by delta tau k, and nxy is shifted by delta x delta y k. And you can check that this term and this term are invariant. What this means is that phi, that started its life here as a real valued field, because of this integer valued gauge symmetry, we can make phi circle valued. We can choose a gauge that phi is always, at every site, is between 0 and 2 pi. Now, this gauge symmetry makes phi effectively circle valued. So now I'm going to follow the same trick I used in the standard XY model. I'm adding a term kappa, the coefficient kappa, sum over the cubes, f squared. I can think of this f as being the field strength or the curvature of this integer valued tensor gauge field. So I'm adding this term to the action, and I'm going to take kappa to infinity. If I take kappa to infinity, I restrict the configurations of gauge fields to those for which f vanishes. And if f vanishes, I can forget about this term and replace it by a Lagrange multiplier, phi tilde. Kappa was a parameter in the theory. Phi tilde is a field that I should integrate over. It lives on the cubes, multiplying that. So we have the same treatment as before. We started with a model with a cosine. We rewrote it in Villain form. This was invented by Villain, maybe 60s or 70s, long before I learned physics. And the only thing we do here is that we impose this flatness condition on the gauge field using the Lagrange multiplier. So, and of course, the Lagrange multiplier was invented by Lagrange. So, this model, I did promise some references during the talk. So, this is the model we're going to study. This model, these two terms exist in the ordinary Villain formulation. They reflect the cosine of delta tau phi and the cosine of delta x delta y phi in the original model. And this is the term with the Lagrange multiplier that sets the curvature to be 0. And this model is well defined. You can check that the functional integral converges. There's a finite number of sites, finite number of links, finite number of plaquettes or in cubes. And phi is the integral over phi and the sums over n converge. And again, we should not integrate over gauge mode, we should not sum over gauge mode, we should only integrate over phi and phi tilde in all the n's modulo gauge transformations. And this is a manifestly convergent integral, so everything is nice. And this model is free because it's quadratic in the fields. And it has the momentum symmetry. You can check that if you shift phi by alpha of x plus alpha of y, these two terms are invariant, and this term is invariant because it doesn't depend on phi. And there is a winding symmetry. I can shift the new field, this Lagrange multiplier, phi tilde, by a function of x plus a function of y, and that's also invariant because it multiplies a total derivative. So these two are exact symmetries of the lattice model. So the new symmetry that we found in the continuum, and one might be some suspicions about it, now it exists already on the lattice. These two symmetries have a 't Hooft anomaly, and the analysis is exactly as in the continuum, except that now everything is rigorous. It's a little bit more writing because we have to keep track of the links and the sites and all that, but it's a finite number of variables, so it's open system. And the spectrum is just as we found in the continuum theory. There are light plane waves and heavy momentum in winding modes. And using Poisson rate summation on these gauge fields, we replace, and this was invented by Poisson, of course, it exchanges these two fields, phi and phi tilde. Phi was the field that started the story. We started with the field phi, and phi tilde was a Lagrange multiplier that we made up in order to write the model in a simple way. Now, the Lagrange multiplier and the dynamical fields are exchanged. Beta and beta 0 are exchanged, and the momentum and winding symmetry are also exchanged. So all these features that we found in the continuum exist already in a completely rigorous treatment on the lattice. So it exhibits all these properties, and when beta 0 and beta are much bigger than 1, it's the same as the nonlinear model with the cosine. So this is all I wanted to say about this model. Are there any questions about that before I continue?
Nadia, I actually have a question. So you did all of this on the sort of in the Euclidean lattice formulation. Is there like a Hamiltonian version of this model that has these exact symmetries?
Yeah, so you can do that in the Hamiltonian formulation, but it's a little bit more writing because here time is discrete. So I can try and take the continuum limit in the time direction without taking the continuum limit in the space directions. That takes a little bit more writing, but it's clear that it's right in the following sense. Once you have a Hamiltonian formulation, there's immediately a Euclidean lattice formulation by just using a transfer matrix that takes you from one value of time to a later value of time. The same thing is true here. We can always go backwards. The problem is that we have all these gauge symmetries and Gauss laws associated with them, so we have to keep track of all of them. And all the subtleties in finding this picture in the Hamiltonian formulation and the anomalies and everything that follows from it are messy. They're still there because it's the same model, but it's but it's a lot harder to keep track of it.
So in the Hamiltonian formulation, I mean, you will have all these exact symmetries. I mean, I guess they're not going to be exactly on site, but because they have to have this anomaly, but you have them.
Well, no, it will not act on site. It
Right.
will not act on site because I will have to do some gauge fixing, and the gauge fixing will lead to a constraint that I will have to worry about that
Right.
later.
Okay.
Another way of saying it is that even the global symmetry, the winding symmetry that I had here, first of all, you could have asked this question already about the ordinary XY.
Yes.
It's a lot easier to work with because we don't have all these subsystems in space and time are treated unequally. And there you could do the same thing. And the issue of on-site, see, for people who don't know about anomalies and all that, they shouldn't be surprised. Okay, so we found an anomaly, big deal. But people who learn about anomalies from the condensed matter perspective, so people who study that from the high energy perspective would be surprised that there is an anomaly in a completely regularized setup. The condensed matter people know anomalies in a completely regularized setup, but only in a Hamiltonian formulation. And there, the main point, so is stated, is that the symmetry does not act on site. Here, in the Euclidean formulation, the system does act on site. However, the action itself, and the action is invariant, more precisely, e to the minus the action is invariant. The Lagrangian density is non-invariant under the symmetry. Under the symmetry transformation, before we start all the gauge fields and all that, the Lagrangian density is non-invariant under the global symmetry. It transforms by a total derivative. A total derivative that integrates to zero, so the symmetry is there. So the analog of what you normally think of as not acting on site is not that the action is not on site, but that the Lagrangian density is not invariant.
Okay, thank you. Other questions?
Yes.
I don't think there's other questions, so please continue.
Okay, so in the rest of the next topic I'm going to go to is making this gauge theory dynamical. So we discussed the subsystem symmetry, and we already discussed what it means to couple it to background fields. And the way we thought about it is that we had matter system, we had global symmetry, and there is a net current. And the gauge fields are such that we couple J times A. That's what we did before. And when we did that, we had this gauge symmetry. A tau goes to A tau plus D tau alpha, and AXY goes to AXY plus DX dy alpha. So what we're going to do now is forget about the system with phi, forget where this thing came from, and just ask ourselves, how should we think of such a gauge theory? How should we think of such a tensor gauge theory? A gauge theory where A has tensor indices, AXY, and in the time direction we have A tau. So that's what we're going to study. And a lot of people have studied this system from many different perspectives. The perspective I'll present here will be different than what's normally being done. So let's start from the continuum. In the continuum, we can write an action. So this is a gauge, this is the electric field. The electric field is a tensor. You can check that it's invariant under the gauge symmetry on the previous slide. And we write an action, and again I'm in Euclidean space, and I write an action. So we write 1 over 2g squared times the electric field squared. That's what we normally write in such cases. And there's also a theta parameter that multiplies EXY. We'll soon discuss that in detail. Since we are in 2 plus 1 dimensions, there is no magnetic field. So if you're familiar with the U1 gauge theory or electrodynamics in 1 plus 1 dimensions, this is very similar. There is electric field, no magnetic field, and the action has a term electric field square, and there is a theta term. So we included also the theta term, but we need to show that it's not a total derivative, and it's clearly gauge invariant, but it's not a total derivative. That's why it's non-trivial. And furthermore, flux is quantized, and therefore it's 2-pi periodic. So we can present this model on the lattice. We should first go to the lattice and make sure we know what we're doing, and then we'll recover these same answers as in the continuum. So there are several ways of doing it. The simplest way is, again, I'm going to use a Euclidean lattice. I can put phases on time-like links, tau, and other phases, uxy, on the spatial plaquettes. So I wrote it here. And the gauge parameters are on the sides. So this treatment is very similar to the standard treatment in the literature of such tensor gauge theories on the lattice, except that most of it is in the condensed matter literature, where people prefer to use the Hamiltonian formulation, and this is the Euclidean functional integral, or Euclidean Lagrangian version of the same system. But I'd like to present it slightly differently. And after hearing me doing it twice, it's easy to see, it's easy to guess what I will do on the lattice. I will simply write this system using a Villain formulation. It's always the same trick. This is a general thing for the students. Once you have a good trick that worked and was useful, keep using it. So that's what we're going to do here. So this is my lattice action. No cosine. No exponentials of things, no nonlinearity. It's a completely quadratic action. I put A tau, which is now real valued, on the time-like links, and AXY in the spatial plaquettes, and I put integers n tau xy on the cubes. And this is the regularized version of the electric fields. It's delta tau of AXY, it's like the derivative, and delta XY of A tau. So this is the electric field, except that we would like things to be, we would like the gauge group to be U1 rather than R. We would like to have this periodicity, and we do that by adding another gauge field, an integer value gauge field, n tau xy. Since we are in 2 plus 1 dimension, we don't even need the indices, but I included them so that it's clear how they transform under various rotations and stuff. And this system has a gauge symmetry. First of all, we have the gauge symmetry of the tensor gauge field, as we discussed on the previous slide. A tau is shifted by delta tau alpha, and AXY is shifted by delta x delta y alpha. So that's the regularized version of what we had on the previous slide. The is also an integer valued gauge field, which effectively makes the gauge group being not R, but U1. This makes the gauge group compact. So all the interesting facts about U1 gauge theory, so when you learn U1 gauge theory as an undergrad, A is real, and you never discuss the fact that the gauge group is really U1, and therefore there are fluxes and magnetic monopoles and so forth. When you're more advanced, you learn about Chern classes, non-trivial fluxes, etc. Our goal here is to understand the analog of that for this tensor gauge, for the gauge symmetry of the subsystem symmetry. And the hero of this story is this integer gauge field, N, and the integer gauge parameter, K. Now, since N transforms like a total derivative, I can add to the action already on the lattice the theta term. So I add on the lattice I theta times this N. So first of all, this N is manifestly non-trivial. Second, it's manifestly an integer because it is an integer. And therefore, theta is 2 pi periodic. So this is my regularized version of the continuum theory I presented earlier. Now, unlike the previous case where we had kappa and a Lagrange multiplier and all that, that was in order to make the integer valued gauge field flat, in order to make its curvature vanish. But here there are no more indices, so there are no more curvatures, so I don't even need to do all that. I don't need the Lagrange multiplier, I don't need this kappa. This whole part of the story is not needed. This is the analog of what we do in ordinary gauge theories in one dimensions, namely in quantum mechanics. Ordinary gauge fields in one dimensions do not have a curvature, and therefore I don't need to constrain the curvature. So that's for these integers. So this is the model we study, and this formulation of the gauge theory is free, it's quadratic. The gauge group is U1 rather than R, that's because of this gauge symmetry with the gauge parameter K. And I added the theta term, which is manifestly non-trivial and manifestly periodic. And you can take the continuum limit, and I'll do that briefly, and realize that this is the same as the continuum theory we wrote down. So what we're going to discuss now, and very briefly because I'm running out of time, is some global aspects of the gauge group, in particular how the flux is quantized, and the defects and operators of the theory, and the spectrum. So we're just going to solve this system. And since we're on the lattice, it's completely rigorous. And since it's quadratic, there's really no obstacle. We just solve everything. We can write it in closed forms, everything we would like to know. And we can do that either in the continuum or on the lattice. And here, the Villain formulation allows us to do everything on the lattice, or we can do that in the continuum, and thus justify everything. In order to make my life easy here, I'm going to do that directly in the continuum. And if it looks slippery, or if you think this is not quite rigorous, or maybe I treated the fields in a careless way, you can repeat this whole thing on the lattice in this Villain formulation, and then everything is manifestly correct. So I'll be very brief. Alpha on the lattice, this gauge, in the continuum, this gauge parameter is 2 pi periodic. And that means that alpha is not just the same as alpha plus 2 pi, but we can put an arbitrary function of x plus an arbitrary function of y, and these functions are integers. So we allow gauge parameters which are discontinuous. This is the first novelty. In this continuum gauge theory, in an ordinary gauge theory, alpha is the map from space-time to a circle. Here, alpha is the map from space-time to a circle, but we allow certain discontinuities. And if you're a mathematician and it makes you feel nervous, say, don't worry, go back to the Villain lattice, the model with Villain, and then everything is completely regularized and you see exactly what we're doing. Therefore, we can have large gauge transformations. And we can have large gauge transformations of this form. This particular functional form appeared earlier when I discussed the winding modes of phi, but now these are the winding modes of phi, are kind of winding modes of alpha, and these are the large gauge transformations that I should include. So there's a little bit of algebra, and you have to use all these delta functions, and this is the answer. And again, this whole thing can be repeated on the lattice, where everything is completely meaningful. And we have flexes. The integral dx d tau of E can have a delta function in y, d tau dy of E can have a delta function in x. And the thing which is quantized is the three-dimensional integral of E is 2 pi times an integer. So if you don't look too closely at the details here, this looks a lot like in ordinary electrodynamics in 1 + 1 dimensions, where this is the integral of the curvature, which is the term plus. Next, we can study defects in this theory. What do I mean by defects? These are the analog of Wilson lines. In ordinary gauge theories, we discuss Wilson lines, and there can be Wilson lines in space, which are interpreted as operators acting on the Hilbert space, or Wilson lines in time, which would be interpreted as defects in the system. This is the response of the system to a probe, massive probe particles. So the simplest thing we can do is just have this thing, a Wilson line. So I'm now in Lorentzian signature, T, I denote T, and I take the gauge field A0, and I'm computing this Wilson line from time equals minus infinity to plus infinity. It represents inserting in the system a massive particle with charge 1 under this tensor gauge theory, and it sits at a certain point in space at all times. In an ordinary gauge theory, we do the same thing. We insert a probe particle like this, and this is a Wilson line in time. This is what the Wilson line means in a U1 gauge theory. And in a U1 gauge theory, the Wilson line doesn't have to be straight in time. It can also move in space by adding a term proportional to a sub x or a sub y. So it can bend in space-time. But in this system, we don't have a sub x, we don't have a sub y. So this probe cannot move in space. It is stuck at one point in time. Using terminology that you heard in other lectures, this is a fractal. So the probe particle of this tensor gauge theory is a fractal. It is stuck at one point in space, and it cannot move in space. You introduce it at some point, and it's stuck there once and for all. It's not that it costs it a lot of energy to move. It cannot move in a gauge invariant way. However, if you have two of them, like you have a dipole, say positions x1 and x2, I can have a more complicated object, two particles with charge 1 and -1 and 2 positions in x, and then they can move in y. This is again a property of in fractal stories. I'm sure you heard about it in the other talks, and this is alignment. So a single charge particle is a fractal, and a dipole of them is a line that can move in y. So this restricted mobility follows from the gauge cycle. Next, I'd like to discuss the operators that act. So operators are Wilson lines, or analog of Wilson lines, at fixed time. They can be extended in space, but they act at fixed time so that they can act at fixed time on the Hilbert space. And since the operator has this gauge field has two indices, x, y, we can make a gauge invariant by integrating it over a strip. A strip that runs over all of y and over a finite extent in x. So the operators are strips, and I'm sure you saw similar operators in the other lectures where we discuss fractals. We also have the gauge invariant electric field, which is a point operator. And these strip operators and operators at the point satisfy a non-trivial algebra. We have strip does not commute with E if they overlap or if they touch, and they do commute if they do not touch. And finally, the spectrum. This is the Lorentzian Lagrangian, and we discussed this term, the theta term, and we can choose a gauge A0. So this is standard way of quantizing the gauge theory. We choose a gauge, A0 equals 0, the temporal gauge, and then we have Gauss' law, it's dx dy of E equals 0, and then we can solve for AXY, it's an arbitrary function of x plus an arbitrary function of y, and therefore there are no local excitations. Again, we take this decomposition, we substitute it in the action, we find this effective action for these modes. And we have the large gauge transformations we discussed earlier, and they make this F. F at different values of X are completely independent. So we have separate rotors at different values of X, very much like what we saw before. But their periodicity is different. We have this delta function here. So the radius of the rotor is infinite. And the spectrum has the following form, lots and lots of states at low energy. In fact, there's infinite degeneracy in the continuum limit, there is an infinite degeneracy. So this theory has a lot of peculiar features. This theory has a lot of peculiar features. It has defects, which are fractons and linons. It has operators, which are strips, not the Wilson line, but the Wilson strip. And it has a very peculiar spectrum, no localized excitations, but we have these states that a lot of states with at low energies or a large ground state degeneracy. Let me skip all that and just make a few comments on what happens when we have a Z engaged. So it's essentially the same as with U1. We can do that either in the continuum or on the lattice. Here is the Villain form on the lattice. We have an action which has integers n, x, y, and tau. I'm going to be very, very brief in another n tilde here. And we have some integer valued gauge symmetry for them. This model has a Zn version of the previous one, which was U1. And we can also do it in the continuum by starting with a U1 gauge theory and Hicksing it down to Zn. So again, I'm going to just flash the answers. I don't expect anybody to follow, except to say that we have fractals at fixed point, very much like the previous ones. And we have these linons that are separated in X and can move in Y. And it's exactly as in the U1 gauge theory I mentioned earlier, except that now the nth power is trivial. Similarly, we have operators. The operators are again Wilson strips. I'm rushing very fast. I'm going to flashing it so that just to give you some, just teasing you and showing you that there's more stuff that can be done here. They are Wilson strips, and they are point-like operators, and they satisfy a peculiar algebra. They either commute or satisfy a Heisenberg algebra, or whatever it's called, proc and shift algebra, when they do not commute. In the spectrum, the analysis is very similar to before. We have a very large ground state degeneracy. Lx and Ly are the sides of the lattice. And this is the number of states on the lattice. So the entire discussion can be phrased either in the continuum or on the lattice. The lattice gives you more confidence that it is correct. In the continuum, once you learn how to manipulate these things, it's a lot easier because you don't have to keep track of all these details. And this looks like a good model for fractons. It's gapped. It has an infinite ground state degeneracy, or very large ground state degeneracy. It has particles with restricted mobility. Only one thing is not good about it, is that it's not robust. We have these local operators that generates the electric symmetry, and this operator can destabilize the model. This model, this operator, if we add it to the action, ruins all the nice features we have. So this is very similar to the situation in a 1+1 dimensional Z-N gauge theory. Some people call it a topological field theory. Some people would not call it a topological field theory. It's topological in the sense that the ordinary Z-N gauge theory in 1+1 dimensions is topological correlation functions and so forth. But condensed matter physicists don't like to call it a topological field theory because it's not robust. It has a local operator acting in the space of ground states. And if we add this operator to the action of the Hamiltonian, we ruin this system. The same is true here. This system is not robust, and I'm just saying it here. I'll put it online so that you can read all these slides if you're interested. And therefore, this system is not quite what we want. However, I'm not going to do it here, but it's already done in the literature. We can repeat the entire story I told today in 2+1 dimensions. You can repeat it in 3+1 dimensions. And it's a little bit more involved, there are more indices and so forth. But most of the subtle issues are exactly as I presented today. And the main thing we learn by going to 3+1 dimension is that this problem of robustness does not exist. And this model, if we just repeat the same thing in 3+1 dimensions, is nothing but the low energy limit of the X-cube model, which has all these nice features. So my time is up, so I'll stop here and ask for questions.
Okay, we can take questions.
Hi, Nadi. I was wondering how RG works in this context of UV-IR mixing that you discussed earlier in your talk.
That's a fantastic question. And the quick answer is that I don't fully understand it. And the more detailed answer is that you could ask, why do we want to do RG in the first place? The reason we want to do RG in the first place is that we have a system at short distances which depends on an infinite number of parameters. All the parameters we can write on the lattice, there's an infinite number of options. And at long distances, we have a system that depends on a finite number of parameters. So our goal is to answer the question, what are the low energy degrees of freedom? How do we describe it at low energies? And what are these finite number of parameters? This comes under the name of universality, and I think I had that at the beginning of the first slide, of the first talk. So universality is the statement that an infinite number of different lattice systems flow at long distances to an infinite number of parameters at short distances flows to a system with a finite number of parameters at long distances. And with this definition, the renormalization group works exactly as expected. And in fact, the whole point of this line of reasoning that I followed in this talk, and I was continued in the whole sequence of papers I've been writing with my fantastic students and postdocs, was to frame this entire discussion in this framework. So let me give you an example that you might be more familiar with. Z-engaged theory appeared in mathematics long ago. In physics, it was first introduced by Wagner in the context of lattice models. Then it had a revival. Various condensed matter people worked on it over the years, and then there was a revival of it coming under the title of the Tori code. Kitaev introduced the Tori code, and that had a huge impact. What's the relation between all of these? So we have Z-engaged theory of Wagner, and the Tori code of Kitaev, and the Continuum Z-engaged theory that mathematicians study. What's the relation between them? The relation between them is very similar to what I've been discussing here. Namely, the Z-engaged theory in the Continuum is the low-energy universal description of all these systems. The Tori code is a particular UV lattice model that leads at low energies to the Z-engaged theory. Wagner gave us another lattice model that has a Z-engaged theory on the lattice. Now, the details on the lattice are different. Wagner had an explicit gauge symmetry. Kitaev didn't have an explicit gauge. He had something that works as if there is a gauge. But if you send the coefficient, so Kitaev, for example, in the Hamiltonian had two terms, if you send these coefficients to infinity, which is what you do, you go to low energies, you restrict these operators to be at the minimum, which is 1 or -1, depending on your conventions, and then you land on exactly the configurations of a continuum Z engaged. So this is the relation between them. So when you ask, how do we do renormalization group here? It's the same thing. There are many different lattice models we could use. All of them flow at long distances to something, and our goal is to describe this something. So the reason I went through all this pain of describing all these continuum models was exactly in order to answer this question.
So Nadi, I was wondering, though, rather concretely, it sounds like you couldn't do momentum regularization to achieve RG because the high energy.
Sorry, Derek, can you just there's something in the, can't hear me?
It's the microphone is at.
Okay.
Maybe the microphone not. That would be better.
Hi, Nadi, this is Mike Friedman again. I was wondering concretely, though, how you would implement RG. From what you said, I don't think you would just integrate out the high momentum modes, because some of those contribute to low energy.
Yeah, that's exactly what I would do. That's exactly what I would do. And in the case of this, yeah, that's exactly what I would do. And you can do that very explicitly in these models by expanding the plane waves. So we should distinguish between gap modes, gap models, and not. So if you discuss this phi theory that I had earlier, there's really no problem. The issue is in models with, like the gauge theory that I mentioned, that has lots of states at low energy, or the ZN gauge theory that has lots of states. Here there's a subtlety, and the subtlety is that the number of states at low energies depends on the number of sites. This is the ultimate UV-IR mixer. I do not know how to think of it conceptually. This is a huge question, but this formula for the ground state degeneracy that can be obtained either for X cube model or for others, I did not manage to do it for all cases, but for many cases I know how to do it with my fantastic collaborators. These formulas have meaning at long distances, and they capture the large L behavior of the microscopic system, including the order 1 correction. So the ground state degeneracy is typically n to the power nx plus ly, etc., plus number of order 1, and there could be a prefactor proportional to L, for example. All these are obtained correctly from the continuum tree. So it's infinite in the continuum, so I shouldn't be able to do that. Strictly in the continuum, it's infinite. I will not be able to do better. But if I regularize it in any natural way, I end up with the correct answer. Having said that, it's extremely unsatisfactory. It's extremely unsatisfactory, and I think what we need is a better conceptual framework to think about such systems. And the main thing which is surprising here, for me, is this UV-IR mixing. So I can say a few words about UV-IR mixing. When you start learning quantum field theory, you'll learn that there is no UV-IR mixing. There's this picture of separation of scales in the renormalization group and so forth, and this has been dominating physics for a long time. In math, it's like saying that the properties of the manifold depend to some extent on the way you triangulate. The result of the integral depends to some extent on how you slice it to little strip to have the Riemann sum. It sounds insane. How can that be? In what sense is the long distance thing? In what sense is the integral well defined? That's personally why I find this subject so fascinating. This UV-IR mixing, and we showed here, especially in today's lecture, but there's a lot more to this story, how it appears in very simple systems. We see the same UV-IR mixing. I also want to emphasize that in some non-gravitational systems that arise out of string theory, there is somewhat similar but quite different UV-IR mixing that comes there. There are also systems which are not gravitational, in which UV modes and IR modes get mixed together. For different reasons, the details are completely different, but if you look at it superficially, it's very reminiscent. So for me, this is perhaps the most exciting lesson from all that we have an innocent-looking system, either on the lattice or in the continuum, and it has this UV-IR mixing. Let me give you one example which is completely different. You can try and ask, let's explore physics at very short distances in a theory of gravity. So how do we explore it at short distances? We pump and pump more and more energy. we have the system, we explore it with higher and higher momentum in order to get better and better resolution at shorter and shorter distances. That's what we have been doing all along in physics. We have a better microscope that allows us to explore things at shorter distances. But when we come to gravity, things are not so simple, because if we try to put a lot of energy in a small region, instead of exploring what happens at short distances, the system creates a black hole. And the black hole is a horizon, and the horizon hides what happens at short distances. And the more energy we put in, rather than exploring the system at shorter and shorter distances, instead we make a bigger and bigger black hole. So this is another kind of a UV-IR mix. So you might say, okay, this is the theory of gravity, we're not interested in gravity, we're interested in systems without gravity. But then there are systems in string theory which have no gravity in it, some limits of string theory that also exhibit such behavior. So for me, the lesson for me, and this is actually the reason personally why I'm so interested in it, is that this dogma that has been so successful for centuries, and especially in the second half of this 20th century and the beginning of 21st century, of renormalization group, separation of scale, and so forth, this thing is breaking down here. And that's why I think your question really hits, this is the main question. How should we think of renormalization group in that setup? So I gave you more than you asked for.
Hi, Nadi, just following up on Mike's question, I mean, it seems like a Fermi liquid would be a good condensed matter example of UV-IR mixing in the sense that you don't have low energy physics at a single point in reciprocal space, but there's a whole Fermi surface worth of points, where the low energy physics happens. And there we do have a good idea of how to do RG. You scale towards the Fermi surface rather than scaling towards the origin of reciprocal space. So is that something that could be implemented for this model, which also seems to have like a codimension one manifold?
Yeah, I'm glad you brought it up. And I don't know if you'll be happy or unhappy if I tell you that a number of people also made this point, that it's similar to that. And especially, there's a series of papers by Shankar from Yale, and there's a version of it by Polchinski, which I really like, in which you try to describe the physics of the Fermi surface using a scaling towards the Fermi surface, trying to follow on the renormalization group picture for these systems. And it looks like this system also has some kind of a subsystem symmetry. A number of people pointed it out, including in these old papers, but more recently the paper by Sentil, Else, and Thorner, who wrote papers on that recently. Superficially, it's similar. The details are completely different. And there are a lot more moving parts in the other system. So I cannot quite distill it in the same way I did it here. So let me get out of this so we can see it a little better. I think this is very interesting, and the fact that it appears in different places, I view that as encouragement that there's something deep going on here which we do not yet fully understand. I do not see a detailed comparison between them. And this is clearly on my agenda too. I would love to have kind of one coherent story that addresses all these special cases of this thing. I do not have it. And the only way I see how to progress on that is kind of working out examples one after the other.
Okay, thanks.
Hi, Nati, can you hear me? This is Zheng Han. Can you hear me?
Okay.
I just want to ask, suppose we apply your formalism to the hard code. What goes wrong?
Okay, I'm totally baffled by it. So I can tell you where it does work. Whatever I said today works for many examples in the literature. It works for the X-cube model. It works for what is called the anisotropic model that some people study. It works for the checkerboard model and for various generalizations of these. The common thing to all of them is that they have subsystem symmetry. The whole story is, the hero of the story is really the subsystem symmetry. And the main thing that makes this picture works is that the subsystem is associated with planes. More mathematically, and that would resonate with your work, we work on a model with foliation. We need to choose a foliation of space-time. And when we choose a foliation, the leaves of the foliations are planes. At least locally they are planes, and then they could twist around and do all sorts of interesting things, but at least locally we have planes. Then I know what I'm doing. So I could do that, and then locally I have coordinate system x, y, and z with leaves in x, y, y, z, and x, z, and run this story. And I still have the discontinuous fields and all the subtleties, but I can more or less manage. Haas code is different, because if there are leaves there, they are not planes. So I'm totally baffled what to do about that. And my take on that is that the models with simple foliations like these are interesting and challenging and so forth, but that's just the tip of the iceberg, because if you do all sorts of other things like Haas code, where that's not the case. And the underlying geometric structure is much, much more subtle. Now, what I don't know is whether what Ha found was the only example in this class, or I don't know if he's there.
He's here.
He's here. He's here. So he could tell us whether this is the only example in this class, or this is the only example that he found, and there are trillions and trillions of them. And the special ones are the ones where they are on the plane.
My short answer, whether there's only one, no. There's no reason to believe that it represents the one exception. Well, indeed, even in the very first paper, I reported several of them, and their subsystem symmetries don't have the same geometry for that subsystem.
If I had to guess with no knowledge whatsoever, if you accidentally found one example, then statistically I would say there must be many others.
Sure.
And yes, we were not clever enough to find tons of them, but I'm sure they're out there.
So, John, what replaces planes in your code?
There are two. So there are generator of the well. So you can specify the subsystem where the symmetry acts, and there is a, well, I would call it the generator of the subsystem. You can, the generator specify a certain subsystem, and you can take a translation of them, or the symmetric difference of the when you take a sum. So it's like a linear space. And that generator is different for all different examples.
But is there a geometric fractal structure that replaces
There is a geometric fractal structure.
So can I think of it as kind of a crinkled plane in some way, or?
Mike, who's talking there? Yeah, I couldn't hear you.
Yeah, that's too bad.
It's okay, just repeat what I said.
No, I think Mike was talking before.
It's a Joe on the mic.
I cannot hear you, and I cannot see you, and I cannot hear you.
I just said that there is a basis of the subsystem geometry. So all the other subsystem symmetry arises by choosing a subsystem where that is chosen by taking symmetric differences of the translation of this generator. And the generator shape, it has no particular, there are many choices. And that leads to the various other models.
How many generators do you need altogether?
Altogether, generator, there are two.
Two generators.
Yeah. So in analogy, the planar subsystem symmetry corresponds to generating three generators along the three planes. And in this case, there are only two.
Okay, other questions? Okay, are we moving straight to Q&A? Should we thank the speaker again?